In our last class, we discussed about RSA cryptosystem, and if you look it carefully, it has basically three different steps. So here the sender is this boy and the recipient is this girl. As I mentioned earlier that to make the infrastructure, the recipient, that means the girl should take the initiative first, that is the first step, that is the setup step. And in this setup step, the girl has to do few things like she has to choose two big primes, P and Q. So the very first question that comes to your mind that how these two big primes could be observed. So the big prime means the primes are almost of this size. So here you can see that it consists of 904 digit long. That means it's around maybe 2 to the power 3000, more than 2 to the power 3000. So the question is, how is it possible for that girl to choose this big prime? Is it really easy or it's really difficult to get this prime? So in this class, I will also discuss about how to get this big primes so that at your own laptop or at your own desktop, you will also be able to find this big number. So this is not a very unique number. So you can find your own this big number very easily. Okay. Then the girl has to make a kind of find this value p minus 1 and q minus 1. That's easy, but the point is the girl then have to find a positive integer e such that e and phi n is equal to 1. That means the GCD of e and phi n should be 1. So the question is, you are dealing with this big number around 900, more than 900 digit long, and that is p. And if you can understand that if you multiply p and q, that is also of the same size, then the size of p and q will be around 1800 digit long. So you are dealing with such a big numbers, and you can understand that phi n is also very big. Then in that case, how to find the GCD of two numbers? So that's also very important. In this talk, we will also describe how we can do it very easily by using some algorithm. Then the girl also have to calculate the value of d, which is the multiplicative inverse of e. So again the same question, how did I get this big multiplicative inverse? That's also very important. And then nothing much. So if she will able to calculate all those values, then certainly she is going to publish this value. So that's not a big deal. Again, if I consider the sender's activity, when he wants to send some message, first he converts this message into this range, but the problem is he has to calculate m to the power e modulo n. So now you can understand that m may not be that long, but this value of n and e could be very long. So they could be very high range values. So the question is how this boy will able to calculate. At the same time, when this girl will receive a message, she also has to calculate c to the power d modulo n, and you can understand this value of d and n is quite high. So the questions are, how did I get this kind of, or is there any simple algorithm which will be able to give you all the result very quickly, very efficiently, so that your small laptop can also do so. Okay, so today's talk is basically based on this, how these algorithms could be done efficiently, that means within the polynomial time. So in this class we will try to explain very briefly what do you mean by a polynomial time algorithm. First, have a look at this. So this is known as primality testing algorithm. That means checking whether a number is prime or not, whatever big it may be. So I will show in this class that there will be some efficient polynomial time algorithm which will able to give you the answer quickly, and that is probabilistic polynomial time algorithm. So we will also explain what do you mean by probabilistic algorithm. Then our very own Euclid algorithm will be able to find the GCD very easily, and also we'll use extended Euclid algorithm which will be derived from Euclid algorithm, that will be also used to find the multiplicative inverse of some element. And finally, applying or exponentiation of something will be done by using square and multiply algorithm. And in this class we will show that all these algorithms are very easy to compute. That means they are polynomial time algorithm. Okay. So first have a look at this Euclid algorithm. So though primality testing is the most exciting portion of this talk, but I will come to it at the end of my talk. But before that, let us first start with Euclid algorithm. Okay. So you all know, if you just search for Wikipedia, you will able to see that he was there around 300 BC, long ago. But he did lots of basic things, and he is considered to be the father of geometry. So you all heard about the term Euclidean geometry. So he is a famous guy. So let us try to explain how the GCD algorithm could be calculated. So if you look at this could be a very simple GCD algorithm. Suppose this is the GCD of maybe 81 and 57, and that can be done very easily. Okay, that you all know. So if you have a look at this algorithmic step, what it says that suppose you have two positive integers whose GCD you want to calculate. Take anything with R0, say A is your one entity and B is say another entity, two positive integers. Then put R0 to be A and R1 to be B, and some counter you set it at 1, and then check whether the remainder is 0 or not. That means you divide A by B and then check whether the remainder is 0 or not. Okay. So start with this, and then you continue the finding the remainder and all. And at the end, when you will find that the remainder becomes 0, it will go out of the loop, and just make the have a look at this counter. So suppose it comes with some value, then go to the previous step, and whatever be the value of Ri, that will give you the value of the GCD. So it looks quite difficult, and you might think that, okay, at that time how Euclid found or how Euclid thought about this process, you may be a little surprised. But in this class, I am going to show you how this can be done very easily and exactly the way that Euclid thought about it. Okay, so just have a look at a very simple demonstration. Suppose I want to find the GCD of two numbers. Okay, so one is say kind of cylindrical thing, which you can see that it's marked with 1 to 16. So it's marked with 1 to 16, and I have another cylindrical portion which is marked from 1 to 10. Okay. So actually what I'm going to do is I want to calculate the GCD of 10 and 16. So I have some unit here. Say it's a kind of, you can see that it's a kind of some mark is there which gives you the unit 1. So 1, 2, 3, 4, 5, 6, 9, 10, up to 10 unit is there, and it is up to 16 units are there. So this unit is fixed. So it's basically repetition of unit 1 to 2 up to 16, and here 1 to 10. Now if I want to calculate these things, so what I did is basically, you can see that say A is 16 and B is my 10. So I want to do a calculation. What I am going to do, what Euclid actually did is this: he actually puts the two sticks side by side and wraps it over another. If it is go out of this, that means it is 6, and if I make a double of it, it will become 12, which is more than 10. So stop it there. So just you wrap it up till it is not crossing the length of the bigger one. So you can see that with just one wrap, it will go out of the range. So you will have to make only one wrap. Okay. So it's here it's 10 and here it's 16. So I just make two things side by side, and then I will cut it down. Cut it down the excess portion. Okay. If I cut it down, then can anybody tell me what is this? The extra portion, what is this? The extra
The
cylindrical.
remainder.
Exactly, very good. So this is nothing but the remainder. Now you can see that both the lengths are same. So both of them are 10 unit long. Now I have, so initially it was 16. Now if I cut it down, then this will be my remainder. So the remainder is now my 6 unit long, and this is my 10 unit long. Now you can understand, if you look at this algorithm, you can see that after doing this, the roles are being changed. Okay. So the role of A and B will be changed. So this is nothing but the remainder, and whichever will be the remainder will now be changed. So now what I'll do is basically the role of this will be changed. So it was the initially in my first step, it was the shorter one, and this one was the bigger one. It has also a 10 unit long length. Now it is the remainder. Now I just change the thing. So now I put it here and I make it a wrap. You can understand that this is 10 unit long and this is 6 unit long. So you cannot have more than one uh, crossing. So just you place one after another and you just cut it from here. So you just cut it from here. So what would be this length? This length will be, now both the lengths are 6. Now this length is 2 and this length is 4. Okay. So this length is 4 and this length is 2. Sorry, this length is 6 and this length is 4 now. So now again you do repeat the same thing, and if you cut them out, then what you'll have? You will have a strip of length 2 at the end. So now it is length 4 and this is length 2. Now you can understand that if you wrap it up, then it will be exactly the same as 4 length. That means when the remainder is 0, so you cannot have any extra remainder. When the remainder is 0, that will be your GCD. So you can understand that the GCD of 10 and 16 is 2, and that was done physically by this strip. So this is the 2 length strip long cylinder. Now this is the GCD of 10 and 16. So that was exactly done by Euclid, and then usually we do, and that can be done very easily. Okay. Now, now I think the idea of how this can be done is quite clear, but it may not be clear that how this is efficient enough. So that will come to after some time. I will show you how and why this GCD algorithm is efficient. Okay. Now let's come to the extended Euclid algorithm. Okay, to understand it quite clearly, let us have a look at this. Okay, so what is then extended Euclid algorithm? For example, suppose again if you have GCD of, we have already seen that GCD of 16 and 10 is exactly 2. So how it was calculated? So I started with 16, I divided by 10. So the quotient will be 1 and the remainder will be 6. Now change the role here. You can remember, now it is the bigger cylinder, it is the smaller cylinder, and we repeat the same process. So 10 was 1 into 6. So it is coming here plus 4. So now you can understand that this is my bigger cylinder and this is my smaller cylinder. So it will come here. So 6 equal to 1 into 4 plus 2. So it is coming here. Okay. Now what I will do? I will do just shift it here. So this is 4 equal to 2 into 2. So this 2 is this plus 0. So the process will continue till we get 0. Okay. So when 0 will come, the last of that step, the remainder will be your GCD. So this is the GCD. Okay. So this is how Euclid thought, and this is considered to be a very efficient algorithm. So what do you mean by efficient? I will come into it very soon. Okay, but before that, let us have another very important result. It says that let D equal to GCD of A, B, then there exist integers U and V such that D equal to AV plus BU. Okay. So if I give you say 10 and 16, and you see that 2 is the GCD of this, can you quickly find some in this form 16 into V plus 10 into u. Can you quickly give me this value of v and u? So that is the point. Okay, so that is actually required while we want to find the inverse of something. So we know that in some n, say if class A belongs to Zn, say Zn star, or suppose if I consider Zn, only Zn ring, Zn plus dot, then class A will have inverse, will have multiplicative inverse when if and only if GCD of A and N equal to 1. Okay. So if A and N, they are relatively prime, then you can always find the multiplicative inverse of A in Zn with respect to multiplication. Okay. So that means if I go with this result, then what we will get? We will certainly find some v and u such that one can be written as AV plus n into u, right? According to this, if the GCD, this is my D, and this D can be written in terms of this. Now, if you make modulo n both side, then what you will get? AV plus NU modulo n, right? Now, if I divide NU by n, the remainder will be 0. That means that is same as AV modulo n. So you can understand that V will be the multiplicative inverse of A. That means A inverse is nothing but your V. So to find the multiplicative inverse, this identity is very much important. So the question is, how do I write this, or how do I get these values of V and U? And extended Euclid algorithm helps us in finding these values of V and U. Okay, so let us have a look at this, the same expression. So this expression was useful in finding the GCD because from this expression we understood that 2 was the GCD. And these same expressions will also help us in finding the values of V and U. Okay, let us have a look at. So from this equation, if I start from here, so 2 equal to, I will just make a backtrack of it. So 2 equal to, how do I write 2? Equal to 6 minus 1 into 4 equal to 6 minus 1 into, now replace this 4 by this 4 from this equation. So what should I write here? 1 into 4, this is nothing but 10 minus 1 into 6. That means minus 1 into 10 plus 2 into 6. You can always check. So minus 10 plus 12, that means 2. Same. Now what I will do? I will replace this 6 by this 6. Okay. So that is minus 1 into 10 plus 2 into 6 means 16 minus 1 into 10. That is equal to, so here 2 into 16. So this is minus 2 into 10 and here. So minus 3 into 10. So you can check, this is 30 and this is 32. So this is 2. So you can understand that. So 16 was my A, 10 was my B, and V was my 2, and U is my, so you can write it plus minus 3. So your U is minus 3, V is 2. So you can write 2 in terms of this. Clear? So this is nothing but extended Euclid algorithm. So the question is, how can I code it? The problem with this kind of understanding is that if you are going to solve this by following this algorithm directly, then the problem is from the very beginning, you will not be able to understand how many lines that you will have here. That means you can understand that you are going to backtrack. That means when you are going to write in this way, you are going to backtrack this. So you are putting this value here, then you are putting this value here, then you are putting this value here. So that means all the important terms will be remembered. Unless you remember or store all these values, you won't be able to substitute. But the problem is, unless you know how many variables that you need to store, it will be difficult for you to understand or to write a program that how many exactly, how many steps you require or how many variables you will be reserved to store all these values. Okay, that's why some other techniques are being used here. For example, here you can have a look at this. This is from my book, Basic Modern Algebra with Applications. If you go 461 page, so there will be a table 10.2. There you will have extended Euclid algorithm, and just one typos is there. It is AU plus BV. It should be AV. So U and V will be just interchanged. Okay, so it should be AV plus BU. And you can see that you will not have to have too many variables. So only this many variables will able to store. That means the next two lines variables will be stored through this. And if you follow this, then you will ultimately find the values of, so this R value is your GCD and this is your U and V. So that the R value can be represented in terms of AV plus BU. Okay. So this is nothing but the extended Euclid algorithm. But now the main important portion is that why these algorithms are efficient. Okay. So to understand that, let us have a look at some other algorithm. Okay. Let us have a look at some primality testing algorithm. Okay. So very naively, if you see that when we talk about in our very say in a school level, when somebody asked whether say n is given something, say 101, and if I ask you whether n is prime or not, how do you check? The simple algorithm would be first try with some I, you take some I, starts with 2, and then try to check whether 2, 3, 4, etc. up to n minus 1, go up to this and check whether any of the i's, whether I divides 101 or not. If you find that no I from this set divides 101, then your conclusion will be the number is prime. So number is prime. But if one of the i's will divide 101, then your conclusion will be the number is not prime. So in that way, if I consider, so if no I from 2 to n minus 1 divides n is prime, else n is not prime. Okay. So one may give you some better algorithm. So here we started with this, and if you go on carrying with this, so for 101, how many steps that you have to check? Because 101 is a prime number, so how many steps you need to check? You will need to check from 2 to 100 many steps. Okay, so how many steps you need to check? Can anybody tell me quickly how many steps he needs to check? So I runs over this to this, so how many steps he need to calculate, or how many steps this thing will be occurring? Quickly.
99 steps.
So this is 98 plus 1, so 99 many steps one needs to execute this step. Okay, very good. So can you give some better algorithm to do so? That one may think of that, why not then from 2 to n by 2? And if no I from 2 to n by 2 will divide this, then n is prime. And if some of the i's will divide this, then n is not prime. Okay, if you know little bit of mathematics, then you can very easily say that, okay, why not then from instead of n minus 1 or n by 2, why not till square root of n? And the same thing. Okay, but if you look at with a specific number, for example, if you take 32771, this is a prime number, then this will execute, this step will be, whether this divides n or not, this step will be executed just 3, 2, 7, 6, 9 many steps, whereas this step will be done around 16385, whereas this will be done only 181 many steps. Okay, since this is a square root of n. So if you make a square root, it will be around this many steps that will be executed. So out of these three algorithms, if I call it algorithm 1, algorithm 2, and algorithm 3, then which algorithm do you think that the best algorithm among these three algorithms? 1, 2, or 3? Which algorithm do you think that the best algorithm for that?
3.
Okay, of course, the 3, because here the number of steps will be less. Okay, so now you have a kind of intuitive idea that what do you mean by a good algorithm, or at least you can have a kind of comparison that which algorithm will be a better algorithm. So with respect to this goodness, something is defined, something, a special term in complexity theory is defined, and that is known as time complexity. So the question is, what do you mean by the time complexity of an algorithm? So here we have three different algorithms, and we want to measure the time complexity of these three algorithms. So one may very quickly give the answer, okay, since the term consists of time, so why not it could be a measure of the time or the amount of time required to execute the algorithms. That may be considered a time complexity of an algorithm. Do you really agree with that? Okay, so suppose I define the time complexity of an algorithm means the time required to execute that algorithm. Do you agree with that definition? Okay, so is it clear to all of you that what I am now defining? I am defining a time complexity of an algorithm by the time, the physical time, by clock. How much time it requires to execute some algorithm, that will be considered at the time complexity of that algorithm. If I define like that, then what would be the problem? Okay, let us have a look. Suppose, so that was the worst algorithm among these three, and that was my best algorithm among these three. Suppose I feed the best algorithm to a very old machine, which takes, say, which has very bad configuration compared to today's configuration. Whereas I feed this algorithm with this input to this decent modern machine. Okay. Now, if I define the time complexity of the algorithm by the time it takes to execute the algorithm, then you can understand that though this is the worst algorithm among the three algorithms, it will take less time compared to this because the specification of the machine was very poor. So it will not perform as good as this machine due to the specification. So here, if I define the time complexity of an algorithm in terms of a time taken by some machine, it will certainly depends on the time, but that should not be the case. Okay. So now, can anybody be able to tell me what should be the parameter that I should take care of while defining the time complexity of an algorithm? Anybody?
So the input size.
Okay, the input size, but input size, how do you define them? How do you define the time complexity? So input size is fine, but how do you do? Here also the input size was same, right? But how do you define then time complexity? What do you think?
How many steps it is executing?
Very good. So now you can understand that if I want to define a time complexity of an algorithm, then the time complexity should depend on something which is inherent within that algorithm. That means it should be something, a part of the algorithm which remains unchanged even if you change the machine. And what remains unchanged? The number of steps that you need to calculate. So here the number of steps that you need to calculate is independent of the machines. Whether you are given this in this machine, that will be calculated same number of steps? Even if you put here, that will also be done this same number of steps. That means the number of steps is basically invariant, or it is independent of the machines. So intuitively you can think of the number of steps that it executes. Okay. So when we call an algorithm to be an efficient algorithm, now the input size plays the most important role. So here the input is this. So what do you mean by the input size? So this is a decimal number. If you convert this decimal number into binary, then it will have some binary representation. So usually it is found that if you have some number n in decimal, anybody be able to tell me how many binary digits are there to represent this decimal number into binary? Around? Any idea? Okay, say let us try to have 5. So it's basically 1, 3. So this is like this. So 1, 2, 4, 5. So this is my decimal number, this is my binary number, and the number of bits here is 3. So size of 5 is 3. Okay. Now if I have say 10, 100, then roughly, very quickly, can you be able to tell me how big is this? Or maybe say I have 2 to the power 10. Rough estimation, quickly. Can anybody be able to, how many bits are required to represent this 2 to the power 10? Quickly you can check. What is 8?
32 bits, sir.
Which one is 32?
2 to the power 10, sir, 10 bit.
So how many bits are
Actually, sir,
required?
sir, 10 bit.
10
2
bit.
to the power
Okay.
10.
Then 2 to the power 3 is how many bits are required to represent? 2 to the power 3, how many bits are required? According
3
to
bits,
you,
sir.
4.
3 bits. Let's see. So this is 8. So this is 0, 2, 4, 8. So it requires 4 bits, not 3 bits. So, but your approximation is correct. It's around 3 bits. So you can think of any number n which is in decimal. If you make a log 2 of that, and if you take the box and plus 1, so log n base 2 may not be an integer, but if you take a box of that, that will be the approximation of the integer. And if you make a plus, so around that many bits are required to represent n. Suppose n is there in your decimal representation, and the number of bits required to represent any n decimal number is this. Clear? You can check it. So say 32. Okay, 32 is how much? 2, 4, 8, 16, 32. 2 to the power 5, right? So you can check that it requires 6 digits, 6 bits. How much? 0, 2, 2, 4, 8, 16, 32. So 1, 2, 3, 4, 5, 6. 6 bits are required. Say 31. What is 31? You can check that if this is decimal, for 31 is 1, 2, 3, 4, 5. Let's check. So this is 1 plus 2 plus 4 plus 8 plus 16. Can you quickly check how much is this? How much is this? Is it 31?
31.
Very good. So in general, 2 to the power n in decimal, 2 to the power n minus 1, not 2 to the power n, 2 to the power n minus 1 in decimal is same as in consecutive bits. So, sorry, how many bits? You can check how many bits. So it is 31. This is 2 to the power 5 minus 1. Right? So this is 31. 2 to the power 5 minus 1 is 31. For that 5 bits were required. So for 2 to the power n minus 1 in decimal, n bits are required. Clear? So that you can understand that if you make a log of this, then something plus 1 will be required. So to represent, so that is very important. That is basically giving you some idea about the size of the input. What do you mean by a size of an input? So some algorithm, if some algorithm is there, you need to give some input and you need to measure the size of the input. Okay. So here also, in case of primality testing, you are giving n as an input. So size of n is nothing but the binary representation of this and then the number of bits to represent n. So that is the size of n. Is now clear to you, all of you? So it depends on every algorithm will have some input, and that size is basically, for example, suppose you want to find say some graph algorithms. Okay, some graph algorithms are there, some graph algorithms say, and your input is say number of edges. So that is your n, and the size of the input is the binary representation, the number of bits required to represent n, that will be the size of n. Okay. Okay, so that's very good. Now let us have another important parameter that is required, that is some notation. For example, in my previous example, so if you go to this example, you can see that how many number of times this operation division algorithm happens, or division checking of this division is happening, is around 32771. Here also around 23, sorry, here also it should be 32. So I have a mistake, it should be 32, it should also be 32. So the number will be around 16385, and here also the number will be around 181. So here it's around a exact number of times, how many times this I will check whether I divides n or not. Okay, but in many cases it may happen that it would be very difficult to find the exact number of times. For example, some algorithm, say some input is there n, and the number of steps it does is like n to the power 98 plus say n to the power 42 plus maybe n to the power 36 plus 7960 n square plus 1. Suppose this is my exact number of times that algorithm runs. Okay, so you can understand that from the expression that it may not be always very easy to calculate the exact number of times that the algorithm runs, or not the algorithm, the testing happens, or the division happens, or the number of steps it executes. So we should have, in computer science, we should have something that will give you kind of approximate value. Now you can understand that if the value of n is quite large, if the value of n is large, then this term will dominate. Suddenly this term will dominate over others. Okay, so you can understand that this term will go much faster than this. So you can understand that if the value of n is quite large, then this term will dominate the remaining. So based on the nature of this term, the whole nature of the whole term will act. So basically this will play the most important role. So based on that, few definition came into picture in the concepts of complexity analysis, and it says that, so the first thing is we need to know the big O notation. So it's a very simple notation. So suppose there is a function from the set of all natural numbers to non-negative real numbers. So it's from natural number to non-negative real numbers. So what do you mean by the order of G? So this order of G is basically a set. It consists of all such functions from n to r star, and there exists a real constant C and n0 n such that the function is basically bounded by the constant into Gn for all n belongs to n0. So looks you quite difficult to understand this definition, but let us have a look at some image. Okay, what it says that suppose some function g is there. Okay, some g n is there. So g is a mapping from n to non-zero real numbers. Sorry, non-negative real numbers. Okay, so some function is there. Say this is my g. Okay, what do you mean by this set? So this set consists of all such functions fn. That means all such functions fn are few functions which may be like this, or maybe like this. You can understand that after this level, all the functions are less than some constant time of the function gn. Some constant time, say this is the original function, say some constant into gn. So all the functions, all the f's after say n0, if you, so this is your n natural numbers, you are placing natural numbers over this, and c is a non-zero constant. After some values of n0, all the function values that is bounded by this value. So big O of Gn consists of all such functions such that there exists a positive real constant c and n0 belongs to n such that this value is bounded by that constant into Gn, but from when? For all n greater than equal to n0. So this value is less than equal to this value, fn is less than equal to c into gn for all n greater than equal to n0. That means it may be, here you can see that the red one is bigger than the black one, but after n0 its value is less than equal to c into gn. Okay, so that's the idea of the order of a function. So that is the big O notation of some function g. So if you look at this, suppose my fn is like n square plus 7n plus say 10,000. Now you see that for all n greater than equal to 10,000, this value is less than equal to 3 into n square. That is, for all n0 greater than equal to, for all n greater than equal to 10,000, and if you consider c to be 3, then you can understand that n square plus 7n plus 10,000 is nothing but order of n square, because you can understand that your gn is 3 into n square, and that is, if I consider n0 to be more than 10,000, then that value is less than equal to 3 into n square. That is why this is bounded by n square. So you can understand that this function equal to order of n squared. So this is not a perfect mathematical notation, but in case of complexity theory, we actually deviate from the notation. It should be this belongs to order of n square. But for the sake of simplicity, we just write this equal to n square. Okay. So now you can understand that if this is your function, then you can understand that very well. We can write it order of 98, right? So in that case, you do not need to find the exact values. So you can provide a kind of expression of this upper bound that will give you the idea. Is this clear to all of you? Is the notation or idea clear to all of you?
So what does the first line imply in the book?
So here fn, here, so according to order of gn, it must be a set, right? It must be a set. So some function must belongs to that set. but we use a different notation. In complexity theory, we use Fn equal to order of Gn. It means that Fn belongs to order of Gn. So it's just a notation. So here you can see that this equal to order of n square. That means this polynomial must be belongs to order of n square. But for simplicity, we write it, this is order n square. So this, the order of this is same as order of n square. So that's what. Now it is clear. So it's just a notation. Clear? Okay. So let us try to, with respect to this definition, let us try to understand what would be the complexity of the very simple algorithm, that is the addition algorithm, say bitwise or the addition, binary addition. So what could be the complexity that we can think of? One of the most simplest operation that we can think of. So suppose this is my 6-bit long a binary string, say A, say 1001111, and this is a 5-bit long binary string B, say 11101. So if you do a kind of binary addition, so what you'll get? I will get 1 plus 1, that becomes 0, and we have one carrier. Okay, so this is my carry bit. So now 1 plus 1, again that becomes 0. I have a carry bit. So again I will have 1 plus 1 plus 1. So this becomes 1, and still we have a carry bit, and then again 0, we have a carry bit, then again 0, we have a carry bit, 1 plus 1, that becomes 0, and this will be finally 1. So this is my addition of these two binary strings. Okay, so this is my, if I consider this is my input, so what is my input size for this? So here it is my algorithm for addition of two binary strings. So this is my algorithm. So this is my addition, and it takes two inputs, A and B. Suppose the binary bit length of A is say K, and say this is L. So approximately, so this is bit length, right? So this is size of A, this is size of B. Approximately, how much do you think that the addition bit operations that you need to execute? How many bit operations that you need to execute? So this is my 1-bit operation. This is my another bit operation. You need to carry, add with the carry again. So here there are two operations, and so on. So in terms of order, can you be able to tell me how many bit operations that you need to do so? Suppose
Next scale plus 1.
okay, if you, so this is, if I consider max of KL equal to say M, or say K is the maximum of this, K and L, K is the maximum. So you say that K plus 1, whatever may be, you can understand that it should be order of K, right? That's why now you will able to justify, or you will able to appreciate why order is important. So you do not need to find the exact number of operations. For example, here we have one operation, here we have 2 and then 3, here we also have 2, here also have 2, 2, 2, and then extra 1. So here you don't have to find the exact number of operations, but you can understand that it would be, it cannot cross much, right? So the number of operations will be around 1 bit more, maybe 1 bit around some constant time, 1 bit more of the maximum bit length. So that means in terms of order, it's very easy that if K is the maximum of this, then the number of bit operations required to do so is order of K. Is it clear to all of you? So you don't need to exactly count the number of bit operations, but approximately it cannot be more than order of K. Is it clear to all of you?
Yes, sir.
Clear? Okay, good. Now, if you consider multiplication, bitwise multiplication, how will you do so? So it's basically the algorithm, if you understand it quite clearly, it's basically, suppose this is your A and say this is your M. So binary representation of N and M, say this is your M and this is your N. How it is done? So if it is 1, if I'm going to multiply it with 1, the idea is you just copy the string, this one, copy N. Say if I multiply with 1, I just copy it like 0, 1, 1, 0, 1, the same thing as this. Okay. If this is 1, again the second bit is 1 here, then what I'll do, I will again make a copy but a shift and put a 0 here. See, this part is same as your this part. Okay. If this is 0, we'll just make all the zeros properly. If this is again 1, the last bit was already 3 were there, so you put 3 zeros here and then make a copy of the first thing. The same thing is here. Okay, and then make a OR of this, make an add of this. So addition can also be done two operand at a time, and so on. So ultimately we'll get this. Now, any idea how much, if this is of say length k and say length l bit? Suppose this is of length k and this is length l. So how many bits will be required? So n say k and m say l. So approximately for multiplication, how many operations that you need to calculate? Any idea? Order of how much? If you look at how many?
K into L.
Exactly. So it should be k into L. Now you can understand that if many zeros are there, then you do not need to do anything, right? So this is your L dash is the number of non-zero things. So then L0 must be strictly less than equal to n. So actually the bit operation will be order of k into L. Okay. So this will be your k into L. So you can have a look at this from my book, and then you will get the whole thing is not very difficult. You just need to check, and then in my book I have given it with details so you can understand it quite clearly. So what is the final outcome is here? For addition, bitwise addition, we require around k. For multiplication, we required k into L. Okay, where k and L are properly defined. Now, similar to this addition, you can have subtraction and you can have division. So you can understand that in multiplication we use basically addition, and in case of division we use basically subtraction. So this also follow the same thing. So if this is k and this is L, and if you want to divide this by this with properly, of course this should be non-zero and so on, then for that the number of bit operations required will also be k into L. Similarly, for subtraction, if you want to say from A to B, if it is k and L, and if the maximum of KL is k, then for subtraction also you will require order of this bit. Clear? Okay. So now we have all the basic operations at our hand, and based on that, we are now going to do the division algorithm and all. Also note that if you have this, like say if you want to have say A congruent to B modulo n. Okay. So can you tell me what could be, who will play the important role for this kind of calculations? A congruent to B mod n. I want to calculate this. So whose bit, which should be my input size? It should be A, B, or n, or all of them. Or if you want to calculate AC congruent to BC modulo n. So you need to think about it. Okay, I'm giving you a kind of homework, or you just think about your own, that which should be the input size, whether it should be the A size, B size, or N size, or any one of them, or all of them, what should be, and what should be this values. Okay, but now based on this, what we'll come to the division, or we'll come to the Euclidean algorithm once again. Okay, so in case of Euclidean algorithm, if you look at this, we have few things that we need to take care about. Okay, first thing is that if a and b are two positive integers, and if a equal to bq plus r, where r and q and r are integers such that this, then GCD of AB is same as GCD of B and R. That's very important. Okay, so if you write something like this, for example, in case of our 10 and 16, so in case of our 10, 16 and 10, what we had our like 1 into 10 plus 6. So this was my A, this was my B, and this was my R. So it says that this result says that 16 and 10 will be same as GCD of 10 and 6. That's why you did the next step. Now the same GCD is there, that's why you just put it here in that way, and you continue till. Okay, so that is very important observation, first thing. So if this whole derivation is done in my book, so if you are interested enough, for math students, they must do it, and then they will realize why Euclidean algorithm is a polynomial time algorithm. Next important observation is that in Euclid algorithm, so they are the different R's. If you do two consecutive steps, so this is Rj plus 1 and this is J. So this is the remainder after, if you calculate two more steps, then from this remainder you will get this remainder in this algorithm, in your earlier algorithm, in this algorithm. So here this I is getting incremented, and you are getting R1, R2, R3, and so on. So it says that if you continue doing that for two more steps, then Rj plus 2 is strictly less than half into Rj. What does it mean? If you go back to the notations, so where I have calculated this value of 16 and all, so where it is, I think it's somewhere anyway. So if you write like this, say 16 equal to 1 into 10 plus 6, then 10 equal to 1 into 6 plus 4, then 6 equal to 1 into 4 plus 2, and then 4 equal to 1 in 2 into 2 plus 0. Okay, so suppose this is your R1 and this is your R2, sorry, R2, and this is your R3. So this is your Ri and this is your Ri plus 2. This important result, very important result, it says that this value Rj plus 2, that means this value 2 must be strictly less than half of Rj. That means half of this is 3. That means this value is strictly less than 3. Similarly, this was your 4, and this value should be strictly less than 2, and so on. And that gives you the nice observation that this algorithm converges to 0 very quickly. Why? Just have a look at this. Suppose, for the time being, suppose that will give you an idea. Suppose somewhere your R1 is 2 to the power, say 6. Okay. Now you can understand that after two steps, this value will be less than how much? How much? It should be less than
Ri by 2.
R. Yes. So that means strictly less than 2 to the power 5. So I'm just considering the worst case scenario. and that will be 2 to the power 4. So it should be strictly less than. It should be after 2 steps, this will be strictly less than 2 cube, 2, 3, then it will be 2 square, then 2 to the power 1, and then it will be less than half, means less than 1, that becomes 0. So from here you can understand that from 6, 2 to the power 6 to 0, it is coming like this. In the worst case scenario, it may be even much faster, but in the worst case, you may require around 7 steps. Around 7 steps, it will converge very quickly. For example, if you start with say 2 to the power 1000, then you can understand 2 to the power 1000 is a huge number. So you can check how much is 2 to the power 1000. 2 to the power 1000 is a very big number. So maybe you can put it here, 2 to the power 1000. So 2 to the power 1000 is a quite a big number, this big number. So you can understand that if you want to do step by step, it will converge within 1000 many steps, even much earlier than that. So for 2 to the power this is a huge number, but it will converge very quickly. You can understand that according to this rule, if it is followed, then it will converge within 2 to the power, I mean, maybe twice of 1000, maybe 2000 steps, because in every 2 steps, it's reduced by half. So around 2000 steps, it will go down to 0. That means it's very fast. So it's a huge number. You cannot calculate by your even supercomputer to that many steps, one by one step. But this algorithm states that it can be converged within maybe 2000 steps, and that's very easy. 2000 steps can be done very easily. That's why that is very efficient, and that's why this algorithm can be thought of polynomial time algorithm. So what do you mean by the polynomial time algorithm then? That is most important part here. So suppose an algorithm is there. So this is my algorithm, and suppose n is my input and input size is say m. So this is my input size. Input size, that means number of bits required to represent n. So this is my decimal number. Okay, so this is my m. Now if the number of steps that the algorithm executes, if the number of steps that the algorithm executes is of order big O of m to the power k. So big O of m, that is size, to the power k for some fixed positive integer k, then we call the algorithm is in this algorithm is called, then we call the algorithm is in polytime algo. Then the algorithm is, then we call the algorithm as a polytime algorithm. Is it clear? So what we need, see, this is order, not exactly. So m is the size of the input. Input was n, it was in decimal. For example, suppose input is 2 to the power 1000. So binary representation of 2 to the power 1000 is around 1000. And if your algorithm runs maybe say 1000 square many steps, then you say that this algorithm is working in polynomial time, which is the size of the input. Is it clear? Now you can understand that this is 2 to the power 1000 and this is say order 2 square. That means this 0. This is a very small number compared to 2 to the power 1000. There might be some constant, say c into this, but that also this is very small compared to this. That's why this kind of algorithms are known as very efficient algorithm. Okay, but if your algorithm is exponential with respect to say some 2 to the power order of m, like this, if your algorithm executes order of 2 to the power m many steps, then we call this algorithm as exponential algo. Okay, mind that here m is the size of the input. So if your algorithm is of this form, then or this many steps is required to execute this, then we call your algorithm as inefficient algorithm, because that requires lots of steps to execute. So we call it exponential algorithm, where this polynomial time algorithm are called very efficient algorithm. So you can understand that m and 2 to the power m, the nature of m and 2 to the power m, if you plot them, some constant into maybe some constant into, if you plot them, you can very easily understand the growth of this m is quite steady, whereas for 2 to the power m it will be like exponential. So the number of steps will be executed very high, whereas the number of steps executed here will be quite less compared to this term. That's why they are called efficient algorithm with respect to this. Clear? Is it clear to all of you? Is it clear? Any question?
Yes, sir.
Okay, now just tell me, in my this algorithm, what is this in a polynomial time algorithm? Is this a polynomial time algorithm? What is the complexity of this?
Is it order of n?
Yes, very good, order of n, but is it a polynomial time algorithm?
Yes, sir.
Anybody else?
Here n is not fixed.
What? Is this algorithm polynomial time? Okay, somebody says this is a polynomial time algorithm. Okay, let's check. So for this primality testing, your input is n, right? So what is input size? What is input size? Just now we have seen that it is log n base 2 of this order. Okay. Now it requires order of n to give you the output. So this is an order of n algorithm. But now let us try to write n in terms of this. Say m is your size. Then what is n? What is n?
2 to the power m.
2 to the power m. So this is same as 2 to the power m, where m is this. Now tell me, what kind of algorithm is this?
Exponential.
So this is exponential. That's why whatever the algorithm you know for primality testing, till now, I have given already 3 algorithms. They are all equally bad. So for 2 to the power 1000 many, see if your n is of this form, then your algorithm will run around 2 to the power this many steps, which is infeasible for even supercomputers to run. Okay, but we need some special type of programming or special type of algorithm which will be polynomial in nature. Now it's clear, all of you, that what do you mean by polynomial time algorithm? So the algorithm that you have already seen for all the three algorithms that we have already seen for primality testing are very, very inefficient because they are all exponential type algorithm, because it should be in terms of size of the input, and the size of the input is m, and with respect to m, this value is 2 to the power m. So they are very inefficient. Okay, so let's have a look at whether the GCD algorithm is also that inefficient or not. What you see here is for every 2 steps, the value of remainder actually gradually decreases, and you can see that you are actually all the time the values of r is going down, because it's strictly monotony decreasing sequence. It's strictly monotony decreasing sequence of positive integers. That's why it will eventually go to 0, no doubt about that. Okay, but the point is how fast it should go. If it will take exponential time, then suddenly it will be considered as a backed algorithm. But this result actually gives you the idea that how fast it converges. Now you can understand that the 2 steps in Euclidean algorithm must result in cutting the size of the remainder at least in half, and as the remainder never goes below 0, okay, the remainder can never be less than 0, it follows that at most 2 log a base 2 many above steps are required. How? You can understand, just now I have mentioned, say if you start with 2 to the power 6, then you can understand after 2 steps it becomes 2 to the power 5, it becomes 2 to the power 4, it becomes 2 to the power 3, and so on, 2 square, then 2 to the power 1, and then maybe 0. Okay, so how many steps? It takes 7 steps, but this many steps, right? And how the 6 will be obtained from 2 to the power 6? This is log 2 to the power 6 equal to 6. Okay, so log 2 to the power 6 base 2, then it becomes 6. That means if you have this is your n, then at most in every 2 steps it becomes less than half. So at most 2 into log, say if this is your n, then log n base 2 many steps will be required to make it 0. Okay, and in every step, what are the things that you are going to do is here you are going to do basically some division, here some division, and here some subtraction. So which one, division or subtraction, which one is most costlier? Division or subtraction? Just now we have seen which one is most costlier. Division or subtraction? Quickly.
Division.
Division is most costlier. So among these two, this will dominate. Okay, and for division, how much, if Ri is say something, Ri has some bits and Ri minus 1 has some bits, then for this it will have at most, it will have suddenly at most how many? So again, as each step involves division and each division involves number not larger than a, okay, it will take another log a whole square bit operation. Just now we have seen that if n is of k bit long and m is say l bit long, for multiplication it should be required k into l. and also in division it requires k into L. Now if both of them, so this is n, so what should be the value of k? The value of k will be around log n base 2 of this order. This is also log m base 2. Now since what you are going to do actually, now since a is larger than b, so a is bigger than b, no number is more than, no arrays will be bigger than a, so all the numbers are bounded by a. So that's what it says, that it requires L into m. So L is log a base 2, m is also k is also log a base 2. That's why this whole square. And how many steps? 2 into this many steps at most. So altogether order log a base 2 whole cube. So this is your input size and this is fixed constant. That's why this is a polynomial time algorithm. Is it clear? Okay, I'm again explaining. So this is your GCD algorithm. Two inputs are there, A and B. Assume that A is bigger. Okay. So what is the size of A? Log A base 2 of order log A base 2, its size, and this order is order log B base 2. Okay. Just now we have seen that in every 2 steps, it will reduced by half. So how many steps that will be required? So your A is bigger than B. So the number A and then something strictly in 2 steps that will be strictly less than A by 2. After 2 steps that will be strictly less than A by 4 and so on. So in how many steps that will come to 0? Remember, that will be in this size. So log A many steps, it will become 0, maybe at most 2 of log A base 2. Okay. And each step, what are the things are doing? And each step, what it is checking? It is checking division and subtraction. Maybe some multiplication also. But whatever may be the case, division and multiplication are taking the major role. So you are dividing and subtracting something from where? So you are dividing and subtracting, so from Ri plus 1, Ri minus 1, etc. But each of these Ri's are strictly less than A or maybe less than equal to A. So none of these values are more than A. So you can understand that here some multiplication is doing, here some division is doing, but all these values, Qi's, Ri's, all of them, they are strictly less than or less than equal to A. So for this product or for this division, what is required? So for division or for multiplication, you require this into log A base 2 many bit operations. So order of this. So this is your dominant. So this term, this division or multiplication complexity is dominating the whole algorithm, either this one or this one. And that value is nothing but log A base 2 whole square. And how many steps you require? You require this many steps. So for order, you don't need to think about 2. So this is order of log A base 2 whole cube. Is it clear? Is it clear? Any doubt? Okay, so if you have any doubt, please have a look at my book. Everything is written with great detail. So you will find everything there. So don't worry. So just have a look at this. The similar way you can also have the extended Euclid algorithm, because as you know, for extended Euclid algorithm, you initially or basically you have to do the division, the Euclid algorithm first, and then you have to backtrack. For backtrack also, you need to just do division and multiplication and some subtraction. So division and multiplication will take the leading role and the number of steps will be the same. So In case of extended Euclid algorithm as well, this is the same complexity. Okay. Okay. So let us now have to come to the square and multiply algorithm. So square and multiply algorithm is basically a simple way of doing things. For example, suppose I want to calculate say x to the power c modulo n. So x to the power c modulo n. So what are the inputs? Three inputs are there: x, c, and n. And it gives you some integer return. Okay. So how to do? So one simple way could be multiply x, 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 c many times, and then modulo n. But the problem would be, if you do this, then you have to do for large n or large c, this value will be quite high. So c many multiplication will be very costly. Suppose your c is 2 to the power 1000, then what will do? You cannot multiply x 2 to the power 1000 many times. So you have to be little careful, or you have to give some other algorithm that will help you in finding these values. Okay, so let us have a look at what are the algorithm. So it's very easy. What it says that first you consider the c. So x to the power c, first you consider this c and make a binary of this c. Suppose your binary of this c is this: c to the power c l minus 1, c l minus 2 up to dot dot c1. This is in binary. Okay. Now have a look at this. Mind that it should be from the left. So for example, suppose you have here some example maybe there. Okay. So for example, suppose 5 is there, or maybe say 6 is there. So the value of 6 is basically 0, then 2 and 4. Okay. So your this is your cl minus 1, cl minus 2, cl minus 3. That means this is c1, c2, c3. So first look at c3. Okay. So it starts with a equal to 1. This is a counter, while I greater than equal to 1. So you can understand that it counter starts with l minus 1. That means c1, c2, c3. So this is c1, c2, c3. So this is your l minus 1. So first you square it. You started with 1. First you square it and put it in a. If ci, if your ci, so it started with cl minus 1, that means c3. If this value is 1, then you multiply with your square. That's why it's known as square and multiply. First you are always squaring. If this value is 1, then you square it. Sorry, if this value is 1, then you square it. Oh, sorry, you multiply it. So if this value is 1, then multiply a with x. Okay. So x is your fixed. So you are not multiplying a with x always. So if ci, this value of ci is either 0 or 1, because it's a binary digits. So if it is 0, then you are not going to multiply, but square is always there. So that's why this algorithm is known as square and multiply. And you see that it is decremented. So I initially it was l minus 1, and then it is I equal to I minus 1. That is, it's get decremented. So you can understand that depending on the binary representation of C, how many steps it will be executed? It will be executed the number of bits of C. So if you represent C in binary, say if L is the number of bits, then the whole algorithm will be executed L many times. Okay. So in other way, log C base 2 many times it will be executed. And in every execution, one multiplication is there. Here also another multiplication is there with modulo n. That means multiplication and modulo n, they are basically based on this a and x. So your x was there, right? Your x is given. So this a term cannot go out of your n because a is always less than n. Okay, so this multiplication will be log n base 2 into log a base 2. Okay, so you can understand that this a value is usually less than n. So you can think of this a value can also be bounded by n. So the whole complexity will be log c log n whole square. Still, this is a polynomial time, something with respect to c. So if you, is it clear to all of you, the algorithm or the complexity analysis? So this is log c into log l whole square. So this is also a polynomial time algorithm. Okay. So any question till now? Then I should stop it here. Maybe in the next class we'll do primality testing.